Hello everyone. I'm going to discuss finite automata with output. Yeah. So in general, we have seen the finite automata, they can accept or they can reject only. But in this category of automata, output can be taken from any alphabet, not necessary that it is accepted or rejected. So finite automata is of these two category. One is finite automata with output, in which we have two machine, Mealy machine and Murray machine. Sometimes we call it Mealy model and Murray model. And in finite automata without output, we have deterministic finite automata and non-deterministic finite automata, and NFA non-deterministic finite automata with epsilon mu. So general, let's discuss about this little bit introduction of finite automata with output, DFA, NFA, NFA with epsilon mu. Then we'll see that how this finite automata without output can be converted into finite automata with output. So this is deterministic finite automata. As we know that in this DFA model, we have a input cell where we can place the string which we want to process, like 0 1 0 0. We want to process this, can go up to infinite, and we call it, this is input alphabet, input symbols. We are taking input from this alphabet only. So and there is a finite control unit. This is just like analogous to control unit of the computer. We call this as a set of states. This finite control unit is having set of states, let's say Q0, Q1 up to and so on, any number of states. Let's say we have final. One state will be acting as a starting state, and any number of state can be acting as a final state. Let's say this is a final state. So how this DFA is working? At a present state, suppose we are at Q0, it will look at symbols on sigma like this input tape. This is our input tape, right? So we will see this symbol, and then finite automata will decide to change the state, and new state may be the original one, and this read write head is always moving in one cell at a right direction. So this is read write head. So this is read write head, right? So this is always moving one cell at a right direction. So what will happen? This will keep moving until we finish this input. After finishing the in symbols, finite automata may enter into the final state. If it enters into final state, that input is being accepted. If it is not in the final state, that means it is going to be rejected. So this is very simple model where it can accept or it can reject the input string. So for example, consider this finite automata where this starting state is also a final state. And you see here, this is DFA on input 1, we are going to Q0, 0, we are going to Q1. And then this is the in DFA actually. So what will happen? Let's say if we are taking input 1 0 0 1 1. So what will happen here? We are at Q0, it will take 1, Q0 1, we are still at Q1, then Q1 0, we are, let's say Q0 1, Q0 1, we are still at Q0, right? So and now Q0 0, Q0 0, we are reaching to Q1, and then Q0 0, we are reaching to Q1, then Q1 0, Q1 0, we are reaching to Q0, and then again Q0 1, still we are at Q1, Q1 1, Q0 1, Q0, and Q0 1 is still Q0. So finally this state is a final state. So that's why this 1 0 0 1 1 input is being accepted by the DFA. So on the other hand, suppose we are taking W equal to 110 here. What will happen? So if we start from Q0, we have to start from Q01. Q01 is Q0, and then again Q01 is Q0, and again then we are going on 0. Q00 is Q1. So we are done with the input. Input is exhausted. See this states. If Q1 is not a final state, so that means this input is going to be rejected. So this is simplest model where input is going to be accepted or input is going to be rejected. So another model is non-deterministic finite automata. Is the same model, is like it just extension of DFA, where if you look at here in the DFA model, actually delta is a transition. This transition function was mapped from Q cross sigma to, we are changing the state. So this was a map from Q cross sigma to Q. On the other hand, in this non-deterministic, this delta is a map from Q cross sigma to any number of subset, right? So simplest way to understand whether a finite automata is non-deterministic or not. Suppose we have Q0, Q1 and Q2, and let's say this is a final state. So if on the same input you are going to Q0, and on the same input from the same state you are reaching to another state also. So that means this is, we are not sure whether we are reaching to Q0 or whether we are reaching to Q0. So this leads non-deterministic nature. So this is non-deterministic finite automata. We are not sure. Let's say this is 1 and 0, this is 1, 0 and 1. Because of this 0 and this 0, on input on state Q0 you are reaching to two states. That's why it become non-deterministic finite automata. So any number of state can be reachable, like here 0 you can reach to Q1 and you can also reach to Q2. So from a particular state on simple input you can generate all the subsets from a, all the subsets of the state can be reachable. So this is more powerful. NFA is more powerful than DFA because this has more computing ability than DFA. For example, look here, Q00, you are reaching to two states. So this is how this transition table is made. Q00 is Q0, Q1, and then Q01 you are not reaching. This is empty, of course, and Q10 is like not going anywhere, and then Q11 is Q1, Q2. So this is transition table representation of the same non-deterministic finite automata. And the third category, which is even more powerful than first two category, is NFA with epsilon mu. Such kind of automata can change the states without advancement of input symbol. Like see here, suppose you are making a transition function like Q0, Q1 and Q2. Let's say this is finite final state, and suppose 0 this is here, and let's say this is epsilon. Epsilon means there is no input, still you are reaching to Q1. Let's say this is 1 and this is epsilon. Let's say this is 2. So what will happen if you see, if you take input equal to 0, 0, 0, this is also going to be accepted. Reason is very simple, that if you start from Q0, take 0, still you are on Q0, and take still 0, you are still on Q0, and take 0, still on Q0. So you know, after this you can have epsilon, epsilon here. So on Q0 you can take epsilon to reach Q1, and then again on epsilon you can reach to Q2, and this is, so this is the final state. That means this 000 is going to be accepted, is a part of the language accepted by the finite automata. So this is more powerful. Here is another example. This is like, see here, Q00, you are at Q0, on 1 you are not going anywhere, Q0 epsilon you can go to Q1. So this epsilon mu, it can be eliminated by just computing the closures, and like this here. Look at here, Q00, you are going to Q0, and on epsilon you are reaching to Q1 also, and on again epsilon you are reaching to Q2 also. So as a result, on Q00, actually you are reaching to Q1 and Q2 together with Q0. Similar thing Q01, there is no transition on Q01, but Q0 epsilon is here, so you can reach to Q1, and Q1, then Q11 is here, so you can go to Q0, and you can go to Q3, and you can go to epsilon and take Q1 here, Q2, and on this one already Q1 and Q01, yes, so Q1 1, and this should not be there. So yes, so this we can compute, we can eliminate this epsilon from there. Yes. So let's move to this our topic of finite automata with output category. So two machines, Moore machine and Mealy machine. So what is actually happening? This is also like 6 tuple as opposed to the finite automata. Finite automata was 5 tuple Q sigma delta Q0 and F. There is no concept of final state in Mealy and Moore model. So this has been deleted. So now this is Q sigma delta Q0, and in this one, since output is not going to be taken from a alphabet like 0 and 1, so this output we can define. We can take output from any other alphabet, and this is output function, right? So in this Moore machine, actually output function is output lambda is function of the current state only. While in Mealy machine, output is function of the current state as well as current input both, right? So this is the basic difference between Moore and Mealy machine. In Moore machine, output function is function of the current state only. There is no effect on the input. While in Mealy machine, output is function of the current state as well as current input. Look at here. So, for example, this is Moore machine. We can represent Moore and Mealy model by two representation, transition table and transition graph. So, let's have transition table representation. We have present state Q0, Q1, Q2, Q3, and this is next state transition delta. Delta remain the same. There is no change in the delta. Output is depending on the present state only. Q0, 0, you are going on Q3. Same thing, input 1 is Q1. This is the delta which we have been discussing in DFA and NFA. This is output, and this output is function of the current present state only. Output is not being affected by input. So what is in output corresponding to input 0, 111. So if you start by here Q0 and 0, Q0, 0 you are reaching to Q3, and then Q3, 1, Q3, 1 you are reaching to Q0, and Q0, 1 you are reaching to Q1, and then Q1, 1, Q1, 1 we are reaching to Q2. So, you know what will be output? Output is corresponding to each state we received. So, what is output of Q0? 0. Output of Q3 is 0. Output of Q0 is 0. Output of Q1 is 1, and output of Q2 is 0. So, this is actually input, and then we are getting this output. We can easily check that 0, 0, 0, 1, 0 is the output for input string 0, 111. So we should note here that, okay, so for input string of length n in Moore machine, output string is of length n plus 1 always. So, and one more important note here is that Moore machine can accept epsilon also. Input can be accepted by the Moore machine, right? Because if you are not inputting anything Q0 epsilon, we are still at Q0. So, whatever output is associated with Q0 is the output of this input epsilon. So this is 2 note. For input string of length n, output is of n plus 1 length. Epsilon empty string can also be accepted by the Moore machine. So another representation is like transition graph representation here. Look at here, Q0, 0, you are reaching to Q3, yes, you are reaching to Q3 here, and output is 0. So output we are writing here, this is the output. And now Q01 you are reaching to Q1 here, still output remain the same. Output is corresponding to in present state. So this is transition graph representation. Look at here, Q1, 0, you are remaining at Q1, 1 is Q2, but corresponding output is written over here in the state itself. So another model is Mealy machine, Mealy model, and same thing as I told you that, okay, in Mealy model, output is always output, this lambda is function of this input Q cross sigma 2, and we are reaching to the particular output symbol. So this output is always function of current state, present state, as well as present input. Look at here, Q1, 0, you are reaching to Q3 and its output is 0. Same thing here, Q1, 1, you are reaching to Q2 and output is 0. Here, suppose input string is 0, 0, 1, 1. What will be output string? You will start from 1. Q1, 0, you are Q1, 0 is Q3, right? And its output is 0. We note down the output here. Then Q3, 0, Q3, 0 is Q2, and note down the output. Q3, 0 is Q2, note down the output 1, and then Q2, 1, Q2, 1 is Q4, and note down the output. Output is 0. And then again Q4, 1 is Q3, and what is output? Output is 0. So for input string 0, 0, 1, 1, output is 0, 1, 0. So in this Mealy machine, if input string is of length n, output string is of also length n. Point number 2, input epsilon is not going to be accepted by the Mealy machine because it is not accepting epsilon input as opposed to be the Moore machine, where Moore machine is accepting the epsilon input. So this is a transition graph representation. Look at here, Q1, 0, Q1, 0, you are reaching to Q3. This is input and this is output. Output is 0. Q1, 1, you are reaching to Q2, this is input and output is 0. So this is representation of the Mealy machine. So what is important? How to convert DFA to Moore machine? In fact, any finite automata can be converted into Moore machine, and in fact we will see that Moore machine can be converted into Mealy machine. So this interconversion is very easy. In fact, if you have finite automata, we can get Moore, and from Moore we can get to Mealy. And how to? And we know that NFA or NFA with epsilon both can be converted into DFA, equivalent DFA. And this DFA can be converted into Moore, and Moore we will see that it can be converted into Mealy. So that means this is Moore and Mealy model, they are more general to the DFA. So how to convert a deterministic finite automata to Moore model is very simple. In this Moore model, output alphabet is only 0 and 1. So if a present state is final, output function is 1. And the present state is not final, output function is 0. That is the only difference. Delta remain the same. Look at here, Q0, 0, you are reaching to Q1 and 1 you are reaching to Q0, because Q0 is final state, so its output is 1. And Q1 0 is Q0 and Q1 1 is Q1, because Q1 is not final, that's why its output is 0. So it's very simple that we can get a Moore machine corresponding to any DFA. But you remember, if we have NFA, so NFA or NFA with epsilon, this must be converted into equivalent DFA before getting its Moore model. So next one is very important, how to convert Mealy to Moore and Moore to Mealy model, right? Let's understand this. Consider this Mealy machine. This is Mealy machine. Previous Mealy machine just we did. So what is happening in this Mealy to Moore? If you want to convert this Mealy to Moore, there is trick of doing this actually. We need to see the next state column. Q3 has only 1 0 output, and this is also having 0 output. So that means Q3 is not going to be splitted into two parts. Let's see Q1. We need to check the next state column. Let's see Q1. Q1 has 1 and Q1 has 1. So that means Q1 is not going to be splitted. So Q1 remain the same, Q3 remain the same. So let's see Q2. Q2 has 1 output here and Q2 has 0 output. So this Q2 is going to be splitted into two parts, Q2 with output 0 and Q2 with output 1. So Q2 with output 0 and Q2 with output 1, right? So let's talk about Q4. Q4 has output 1, Q4 has output 0. So that means this Q4 is going to be divided into two output, Q4 0 and Q4 1. So two output corresponding to 0 and 1. So we are going to split Q4 into two category, Q4 0 and Q4 1. So that means number of state in corresponding Moore machine is more than number of state in Mealy machine. We want to normalize the number of states, right? Same thing here, Q1 is Q3, transition remains 0, same, and Q2 0 is same as Q2 transition, is Q1, and you are not splitting Q1, so it remains the same. Q2 1 is Q4, Q4 has been splitted into two parts with 0 output and 1 output. So whenever you are writing Q2 0 here, this Q4 0 will be here, Q4 0, because this Q4 correspond to 0 state, right? So now Q2 1, yes, so same thing, Q2 1, transition remain the same, Q1 and 1, and then Q4 0 and 0. There is no change in the transition. Q3 remain the same, Q3 is Q2, but you remember Q3 is Q2, Q2 has 1 output. So this will correspond to Q2 1. And then Q3 1, Q1, this has not been splitted, so it remains Q1. So now Q4 0, Q4 is going to have two rows, Q4 0 and Q4 1. So Q4 transition remain the same. This Q4 has been splitted into two parts. So Q4 1 output 1, Q4 1 output 1. Now Q4 1 is Q3, Q3 remain the same. So this will be Q3 0 and Q3 0. So this number of state has been increased from Mealy to Moore. So this is the one. What will happen? You just write down this only and write down this only, right? So Q3, Q1, we are done with this part. How to get this output part? Look at here. Look at Q1 here in the next state. Q1 1, Q1 1. So output of Q1 is going to be 1. Look at here now. And then Q2 0. Q2 0 is here 0, and in fact Q2 0. So this is going to be Q2 0 is 0. Same thing, Q21 is going to have 1, Q3 is going to have 0. Look at here, Q3 is 0 and Q3 is 0. So output of Q3 is 0. So Q4 0 with output 0, Q4 with output 1. So this is our Moore machine. But we notice one thing. Remember, this Moore machine should be equivalent to the Mealy machine. But here you see Q1 an input like epsilon, Q1 is accepting the epsilon. But our original Mealy was not accepting any epsilon input. So what is solution of this? That we have to add another state. This is the original one. Add another state with the same transition with no output. Look at here. So we are adding another state which is not currently in this state. So Q0 and transition remain the same, Q3 and Q2 0, and its output is not 1, it should be 0, because your Moore machine should be equivalent to the Mealy model. Had it been, it is not coming 1 here, we will not do anything. If we are adding another state because of the situation that we are getting like 1 output, because your model should accept the same input. Okay. So another conversion is Moore to Mealy machine. This is Moore machine is very simple conversion. Transition will remain the same. Transition remain the same. As we know that Mealy machine output is function of the current state, output is current state plus current input symbol. So what is happening here? Q0, Q3. So what is output of Q3? Output of Q3 is 0. So we will write 0 here. And here Q01 is Q1. Q1 is here. So what is output of Q1? Output of Q1 is 1. So that is why it is treated as 1. So same thing over here, Q1 1 0 is Q1, but output of Q1 is 1, so you write here 1. Q1 1 is Q2, output of Q2 is going to be 0, so I'll write down 0 here. So by this way, Moore will be converted into Mealy. Same thing, yeah, we can do this, yeah. So there is equivalent conversion. So one thing you should notice that while converting from Moore to Mealy or Mealy to Moore, number of states can be redundant. That can be minimized, right? Consider this Moore machine. If you convert this Moore machine to equivalent Mealy machine, you will get this. Because this is Moore machine Q1 0. And you are getting Q1, output of Q1 is 0. So this is how it is being converted. Same thing Q1 1. Q1 1 is Q2 and its output of Q2 is 0. So you are writing here. So Q2 0 is like Q1 and output of Q1 is 0. So we write Q0 here. Q2 1 is Q3 and its output of Q3 is 1. So we can see this as 1. So now Q3 0 is Q1, output of Q1 is 0. So this is how we are writing 0 here. Q3 1 Q3 and output of Q3 is 1. So if you remember here, like see, look at here, Q1 0 Q3 1, Q1 0 Q3 1. These two states, these two transitions are the same. So these transitions can be combined together. These two transitions can be combined together. So if you combine together, this Q2 and Q3 can be written anyone, Q2 or Q3. Any occurrence of Q3 in right will be represented by Q2. So here, look at here, this Q3 will be represented by Q2. Rest will remain the same. So this can be minimized. So let's have another examples. This is like Mealy machine. You see here Q1 0 going to Q2 and output is Z1. So this is the transition graph of the Mealy machine. If you just check it into the transition table, you will get this Mealy machine. So after getting this Mealy machine, if you convert into Moore machine, look at here class, Q2 has output Z1 and Q2 has output Z2. So that's why Q2 has been divided into two categories, 2.1 and 2.2. Same thing, Q3 has output Z1 and Q3 has output Z2. So Q3 is being divided into 3.1 and 3.2. By converting into like Moore machine, you will get that there is no output corresponding to Q1. So that means this is your final Moore machine. Final Moore machine, it is having the same answer. So we are not going to add extra states. So these are some references: John Hopcroft, Jeffrey Ullman. You can follow KLP Misra, N. Chandrasekharan, or Peter Lynch. So anyone you can follow. Thank you.